Hello and welcome to StudyLab. This is Victor and we're back with another episode of how to make an operating system. We're already at part 5 of our series and there's a ton to talk about today. So let's see how this goes. I made plenty of changes here to our previous code, so I'm going to discuss everything that I did. First of all, just a quick reminder that we're in 16-bit mode right now, or real mode, and we're working with segmented memory. And segmented memory is basically just a way to access a larger span of memory by using 16-bit registers. So normally if you use a flat memory model and you try to access memory locations, you will only be able to access from 0x00 up to 0xFFFF, which is the maximum word, basically the maximum number that a word or a sequence of 2 bytes can contain. Now this is not a lot of memory, so Intel came up with the concept of segmented memory, and for that you would use 2 CPU registers. One of them is called segment register and the other is used as an offset or effective address. So segment registers were DS or the data segment, CS or the code segment, ES or an extra segment, FS and GS, which were also extra segments. So obviously the DS or data segment was used to access memory locations in your data segment or variables, CS for code, and ES for any extra stuff you might need to address. And when you use segmented memory locations, if you have, let's say, this here, which is our standard location for the bootloader. The way the CPU translates this is it multiplies the segment, so 0x07C0 by 16, and then it adds this offset, which in this case is 0. Okay, and then that result is the basically the final memory location that the CPU uses internally. So in this case, when you multiply by 16, you basically shift 1 nibble to the left, meaning 07C0 becomes 0x7C00, right? We shift all of this to the left 1 digit or 1 hex nibble, and then we zero fill the spots to the right. Okay, and if you don't believe me, just do the math and you'll see that I'm right. I'm always right. And the result is obviously this 7C00, which we said last time that is the equivalent of doing this, using 0 as a segment, so 0 times 16 will be 0, and then adding this as an offset, 7C00. Okay, so that's a short reminder on segment registers and segmented memory model. Now let's talk a little bit about the jump instruction and far jumps and near jumps. The jump instruction is basically just a way to jump, obviously, to a different location. So to an instruction located at a different memory address. So for instance, let's do a near jump. A near jump means jumping within the same segment. So right now we would be in the code segment, in the text section. So we could jump to start here, which is a label we defined. And if we do jump start, what the CPU does is it updates the IP register. Let's add this as a comment. And it sets it to start without changing the CS register, the CS CPU register or the code segment. So it stays within the same segment, the same code segment, but it changes the instruction pointer to point to this. And basically in the next cycle the CPU simply executes whatever is at the memory location pointed at by the instruction pointer. So that's pretty simple. It's basically just a go-to statement if you're familiar with the basic language syntax. A far jump also changes the segment. So it's usually a jump to a location that is farther out. That's why it's called a far jump. And the syntax is basically just the segment and then colon and your offset. And then here, as you can see, I added a comment that this forces CS to 0x07C0. So it actually changes the code segment. CS equals 0x07C0. And it also makes IP equals to start. Okay? Now, why am I doing all of this? Well, remember that I said last time that some BIOSes load your bootloader at this address here. So they use 0 as a code segment and 0x7C00 as an offset or effective address. But other BIOSes will use 0x07C0 as a code segment and will use 0 as an offset. So even though these two things are equivalent, this can cause us some trouble sometimes when we reference memory locations in our code, like when I'm referencing this variable here. And especially if we use segments along with that offset, and we're not sure if the offset is 0 based or relative to this. We can have unexpected behavior. So that's why it's a good practice to enforce your code segment and instruction pointer at the start of your bootloader and basically standardize things. The problem with just using this far jump here is that if the BIOS loaded my bootloader here, with 7C00 as an offset or initial IP, then when I use my start label here, the start label will be relative to this. So the start label would be, let's say, if it's relative to 7C00, then it's obviously greater than that, so it's something like 0x7C10, let's say. So I'm actually jumping to 0x07C0 and 0x7C10, which will be a different location than my start label, because if the BIOS loaded the bootloader here, the correct location is 0x0000 as a segment, and then this offset instead of 0x07C0 0x7C10, okay, that I'm using in this jump. So in order to avoid this issue, I'm using a net-wide assembler directive called ORG, standing for origin, which tells the assembler to force our IP to 0x00. So even though the BIOS loads my bootloader here, once the code starts, we will be forcing the instruction pointer to 0x0000, and then this jump here will make perfect sense because the start label will be relative to 0. Okay, I know that sounds complicated. Hopefully you understand what I mean. If not, maybe replay the video. Or if you still don't get it, just drop a comment below and I'll be happy to explain it in more detail in writing for you. So that was the far jump. And oops. Let's see, I don't know what happened there. Okay, so that was the far jump, and as you can see, I created another label here below, and whatever happens here up to the start label will never get executed as code, since we're jumping directly to the start here. So all of this is basically ignored by the CPU. And the reason I moved these two variables here above is that that's the usual way to do it in higher level languages. So if you're familiar with C# or Java or stuff like that, then it's easier to read code when you have your variables defined before the actual code. So it's just a way to make the code prettier. Now we have one other assembly directive that we're using here called align. And this calls for a short discussion on memory alignment. Okay, let's close this for a bit and let's take a look at our... No, actually, sorry about that. Let's first comment out these lines. And I never mentioned this before, but I guess you figured it out by now. Using semicolon, you can comment a line, or you can add comments within your code. So I'm using this align directive 3 times. I'm commenting it out and I'm building the image again. And now let's take a look at our binary in hex. And just take my word for it now. We're not going to get into machine code, but what I'm selecting here is our for jump, and then our string begins this part here. And yeah, if you count 1, 2, 3, 4, 5 characters here, and 1, 2, 3, 4, 5 bytes here, you can see that for yourself. So our string here starts with the index 5, basically. It's the fifth byte if you start counting from 0. So this is 0, this is 1, this is 2, 3, 4, and 5. So that basically means that our string variable is oddly aligned, meaning it starts at an odd boundary. And CPUs have this odd quirk in that they take longer to read data from odd memory locations than from even memory locations. So if our string variable started out with index 6, it would take less time for the CPU to access that variable than it takes the CPU right now when it's unevenly aligned. And usually it's best to align your variables or your code based on your CPU architecture. So if you're or based on the CPU mode, better yet. So if you're in real mode or 16-bit mode, 16 bits means 2 bytes, obviously. So it's best to have your data 2-byte aligned. Basically, the starting index for a variable must be divisible by 2. So by using a special assembler directive, it is possible to align a variable on a 2-byte boundary, or move it from here to this boundary. Basically enforce it to start with index 6 instead of index 5. So let's close this here, go back to our code, and uncomment our align instructions, save, rebuild, and once again take a look at our binary. Okay, so as you remember, this was our far jump, and 4D was the start of our string, and you can see it here as well, 2, 4, 6. So our first string character starts out at index 6 now instead of index 5. So it's 2-byte aligned. And our index 5 byte was filled with the value 90. Now 90 in hex or in machine code is NOP, or the no operation instruction, which the CPU basically ignores. So what the align directive does is it basically fills your it fills bytes with 90 or the NOP instruction until it gets to X byte boundary. Obviously, you can align your data or code to whatever boundary you want. You can use a 4-byte boundary or 8-byte boundary or 16-byte boundary or whatever. But for our bootloader, we are using a 2-byte alignment. Okay, so we have our variables label, which isn't necessary, but it's just a way to make the code easier to understand when someone else looks at it. When you see here variables, it's obvious that what follows are your variables. And then the align to directive, which aligns the next data on a 2-byte boundary. And here we have just a loading message, which is defined as a sequence of bytes or characters, and it's just a message: Mandarina booting up, please wait. Mandarina will be the name of my little operating system. And then it's just followed by the hex representation of a carriage return and line feed. So basically a new line. Then we have a new align directive, so that our next variable is also 2-byte aligned, and this is just a word variable with the value 38, holding the length of all this string. And then we have an interesting thing called an include. I'm not sure, but I think we briefly touched upon this previously in a previous video, but it's pretty simple. Percentage sign include, and then you type in your file name enclosed in quotes, and this is just a way to include a separate file within your current file. So it helps to keep the code neat and tidy, and not have to type in 100,000 lines of code in a single file. You can modularize your code using includes. So let's take a look at that include. Vim, I added it in a folder called boot_include, and it's named VGA NASM because it has to do with the video graphics array standard, which is just an old video standard that basically helps with managing the video mode, switching from text modes to graphics mode, and so on. Let's take a look at these first, the defined. These are all assembler directives. They're not assembly instructions. And the percentage define directive is a way to define constants. So this is the name of a constant, black_bg for background, and this is the value of the constant. Okay, so what I'm doing here is I am defining some of these bias color attribute constants that I referenced in the previous video. And black is 0 in hex, white is F in hex, or 0x0F as a byte. Red is 0x04, and green is 0x02. So I'm defining those 4 constants. Yeah, and as you can see, the first one is for background, because for now we're always using a black background. Those other 3 I'm only using for the foreground or text color. So okay, what next? Let's see. I have two other constants here which define the BIOS VGA video mode. The first constant I'm naming small text mode because it refers to this. So what the small text mode constant refers to is this text mode, which provides basically 25 rows, 40 characters each, and 16 colors, and 8 pages basically. So you have 8 pages, 40 by 25 characters each, and you have the ability of using 16 colors, which are these colors here. Then we have the wide text mode constant, which refers to this. It has the value 3, and it's also text mode, 80 by 25 characters, 16 colors, and also 8 pages. For now, we're not using the graphical mode, so I haven't defined that. But anyway, for convenience sake, let's just add it in here as well. Define graphical mode 0x13 and save. And then we have two macros. Now, macros are really important and really interesting. They look like functions, but actually they're not. So the way you define a macro is by using the percentage macro directive and then ending it with the end macro. So you have percentage macro space and then the name of your macro, which in this case is BIOS set video mode, and then the number of parameters you want to use with this macro. And then within the macro and end macro keywords, you obviously add your code. And the way that you call this macro basically is by just typing in its name, BIOS set video mode, and then the list of parameters separated by commas. So in this case we just have one parameter. So for instance, if we want to set the video mode to graphical mode, we would just call BIOS set video mode graphical mode, and that would set the video mode to graphical mode. And as you can see, within the macro code we have a %1 here. This is how you basically reference the parameters. So %1 means we are referencing the first parameter passed on to this macro. Okay? That's pretty easy to understand. Now the difference between a function and a macro is that a macro basically is a pre-processing directive. So it doesn't get compiled as a function and a function call. So when you add BIOS set video mode in your code and you compile the code, then or assemble the code, better yet, what the assembler does is it basically copies this code here and automatically makes all the replacements for you. So the final code that gets assembled into a flat file would be this here. okay? Which means if you make multiple macro calls, then this code gets copied multiple times. So it has the disadvantage of occupying too much space in some instances if you do multiple calls of the same macro, but it also has the advantage of speed, because a function call is much slower to execute than the equivalent macro. That's because a function call actually has to push some parameters to the stack or some registers to the stack, so it has to work with memory before executing the actual function, and then you have a call or a jump to the memory location of your function. So the function will save you space in your code, but it will not be efficient. The macro will not save you space, but it will be very efficient to use. Now, for the BIOS set video mode, for now we're just calling it once, so it's a good idea to use a macro for that. Okay, now the code itself is pretty simple. We set AH to 0 because that's the way that we tell the BIOS that, hey, we want to set the video mode. Then we set AL to the desired VGA mode, and then we call the BIOS interrupt 10, and then the BIOS takes care of all that for us. And also the neat thing about setting the video mode is that it will automatically clear the screen for us. Okay, and then I basically moved the code that we briefly discussed last time to print a string on the page. I moved it to a macro as well. Let's keep the comments here consistent. Okay, so for the BIOS subfunction, to write a string on the screen, we have to set ESBP to the location of the string we want to write on the screen. Now, ES we are already setting up within our bootloader at the start of the code before we call this macro, so there's no need to set it up here as well. So here we're just setting up the base pointer or BP register to the first parameter, and the first parameter that we're going to pass to this write string function will be the basically the label referencing the memory location of the string we want to write on the screen. Then 0x13 into AH, that tells the BIOS that we want to write a string, so it's basically just a way to tell the BIOS what function we want to execute. Into AL we move 1 to tell the BIOS that we want the cursor updated after writing the string on the screen. BH will hold the page number. BL will hold the color attributes. CX will hold the number of characters, DH will hold the row number, and DL will hold the column number. And then we finally call BIOS interrupt 10 and end the macro. So that's all for our VGA include. Moving back to our main bootloader code here. So up to here, we should be pretty comfortable with everything that's happening. And then finally we have our main code. We use the align directive to 2-byte align the code, and then we set up our segment registers. We need to set up the ES register because that's used by the write string macro to reference the string that we want to write. So we move the contents of the AX register to ES, and the contents of the AX register is our code segment, or CS. And since remember that at the beginning we're doing this far jump here, our CS or code segment will be this 07C0. And that's what we want our ES segment to be as well, because that's where the BIOS loads our bootloader. Okay, and then we also set the data segment to AX, to AX as well. Okay, and then we finally use our two macros. BIOS set video mode, we set it to wide text mode. We want to use 80 by 25 characters per page and 16 colors. And then we call the macro to write a string, and then we provide the list of parameters separated by commas. The name of our string, the length of our string, the page number, the row number, the column number, and finally the color attributes. And this is interesting because instead of using ugly numbers, we're using our constants that we defined before. And the pipe is used to do binary OR. So here we have black background or green foreground. Let's take another quick look at our include and see what those variables were. So black background was 0 and green foreground was 02. Okay, so we have 0x 00 or 0x02. And if we turn that into binary, it will be 1 byte, so 0000, 8 bits, or sorry, let's lose this because that's for hex and this is binary, or and 2 is 4 zeros and then 0 0 1 0. Okay, because, well, you know why, or you should know why. And let's add these below each other. So what the OR does is 0 or 0 means 0 because none of those are true or 1. So 0 is another way of saying false, and 1 is equivalent to true. So false or false is not true. Two false statements, for instance, cannot be true. They must be false. So this is 0. 0 or 1 is 1. So if you have two statements, one of them is false and the other one is true, and you say A or B, A or B is true because one of those two is true. So the truth table for OR is if you have 0 and 1, and here 0 and 1. 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. This is called a truth table, okay? And basically this truth table is applied to each couple of bits here, okay? Then you do the same for all of these bits. This 0 with the 0, this 0 with the 0, and so on. All of these will be 0 since 0 or 0 is a 0. Okay, so the result is this in binary or 0x02 in hex, which is also 2 in decimal. Okay. And that result is basically a green foreground, green text, and a black background, okay? Which is exactly what we were trying to accomplish here when we did black background or green foreground. It can be a little confusing because what we're actually trying to do is to say we want a black background and a green foreground, but the way to accomplish that in binary is by using the OR binary operator. And in case you don't remember from last time, for the BIOS color attributes, the first 4 bits in that byte refer to the background, and the other 4 bits refer to the foreground. Okay. And then finally we have our hang instruction, basically just a jump back to the jump itself, and our 0 filler here, which fills all the rest of our bootloader with zeros until we get to the 511th byte. And then we have our magic number, or 55AA in hex. Okay, let's clean some stuff up here. Discard and exit this, and now let's clean and build, and then let's try to execute our bootloader again. -FDA for floppy disk emulation and boot.bin. And we get this beautiful loading message here. Mandarina booting up, please wait. So this is the beginning of a beautiful project. I hope you enjoyed all of this and found it useful. Don't forget to subscribe below and hit the bell so we can stay in touch. And until next time, have fun and keep studying.